to continue talking about crystals, crystal structures, we're going to do a quick review here, and we're going to talk about graphite. As we talk about graphite, it's going to be a specific example. We're going to talk about a lot of things that we've discussed previously, maybe hint to some things that we will talk about as we get further into the course, and hopefully start putting some of the theory into action, what's happening. So graphite is made of pure carbon, and there's actually other materials out there that are made of pure carbon, such as diamond. Carbon, in the case of graphite, is sp2 hybridized. In the case of diamond, it's sp3 hybridized, and that is the difference between the two materials, is how they're bonded together. In the case of graphite, all the bonds that it has, and there are 3 bonds per carbon, or there are 3 carbons bonded to each other around a centralized carbon, are covalent. And one of those bonds is a double bond. So it has 2 single bonds and a double bond. I'm going to go ahead and start drawing a picture down here. But what I want to do is I kind of want to start talking about some of these things. That double bond is there's going to be a delocalized electron there, and so maybe that could get you thinking about what the electrical properties of graphite are compared to that of what diamond might be. They are made of the same material. They do have a different bond structure because one's sp2 hybridized and one's sp3 hybridized. The difference between that is we have a delocalized electron, so that can get you starting to think about maybe some things that are coming down in the future about how our theory and how bonding of materials could relate to properties. So I have this carbon, and it's going to be bonded to 3 other carbons. Now, if I was looking exactly top down on this, it would be symmetrical. I'm kind of doing a bird's eye view, so I'm kind of looking at it from an angle, not directly on top. And if we keep bonding these together, we're going to end up with a structure that looks kind of like honeycomb. It's going to have all these hexagons on here. I'm going to draw a few more in. And you might have to use your imagination a little bit here because my drawings, of course, are not the best. And so what we have this plane, this 2-dimensional layer of graphite, and all of our electrons have already been used for bonding. And so the question here is, how can I stack these planes on top of each other, all these layers up, to actually make a 3-dimensional material? How does 3-dimensional graphite actually get formed if we have no more electrons for bonding? And so this is where the last video, a couple videos actually, the past couple videos, we stack these planes up to make 3-dimensional materials. And a couple videos ago, we were talking about van der Waals forces, and that's what's going to go on here. I'm going to have this second plane of graphite, and it's going to be bonded in the same way. These are all covalent bonds, and at each one of these junctions there is a carbon atom. These carbon atoms are going to be attracted to each other through van der Waals forces. And so I have a van der Waals attraction between these 2 planes. So now the question here is, all right, so I have these planes stacked together. The covalent bonds are very, very strong. The van der Waals forces we've mentioned aren't as strong. So if we were to take this into the next step and think about it a little bit further, we know that the close packed atoms and the ones that are bonded more strongly together are more likely to stay bonded together when a material is deformed. If we put enough force onto this, if we apply enough force, let's say a tensile force, we're trying to pull this apart, we know that bonds somewhere are going to break as it deforms. In this case, what's going to actually happen, the bonds that are going to break first are going to be these van der Waals bonds. They're weaker, they're not as strong as the covalent bonds, so as we apply this force, what's going to happen is these planes are actually going to slide apart. And that's what's going to cause the material itself to deform. So when there is permanent deformation of a material, this implies that the atoms within the material has moved. Anytime you bend anything and it stays bent, you take maybe a spoon, you bend it. What's happened is you have actually moved the atoms within the material and you've put them into a new location. The mechanism for this deformation is atomic slip. Slip occurs between two planes, and the planes with the least number of bonds are the ones that are going to, well, the planes that are bonded closer together are going to stay intact, and so bonds between those planes is where slip's going to happen. In this case, the bonds, the covalent bonds, are the strongest, and so the slip between the planes is from the weaker bonds. Now, this isn't always the case because in some cases we don't have van der Waals bonds. We might have covalent bonding throughout the entire material. And in that case, what is the direction that is going to slip? That is where we were talking with our crystallographic notation. We want to know which atom at any point in our material has the most nearest neighbors and the most closest neighbors, the most closely bonded, because in that case it's going to be the strongest plane is going to be in that direction. And so in directions where there's fewer bonds or the bonds are further away, that is going to be where the slip is going to occur. We're going to move on into single and polycrystals. A single crystal is a material where there is the same long-range order throughout the entire material. So from one end of the material to the other end of the material, in all directions, we have the same order. The polycrystal is similar but a little bit different. It has the same long-range order throughout an entire grain. Each grain might be oriented differently, and these grains can have the exact same structure, they just don't line up. So here's a picture here. We have nucleation. We have spots when a material starts to crystallize, when it starts to solidify. And in this case, it's crystallizing, so they are starting to solidify in some type of order. And it started to solidify and crystallize in different locations. And so as these crystals begin to grow, as they spread out, they're not lined up. So as we have growth, and we see that in picture B here, they continue to get larger and larger. We see that there is order, but we see as we get to picture C that when they meet up, they're not going to match up perfectly. If we could reorient these, we could see that we could make a perfect crystal out of all of them, but they're not. They're rotated, they're at different angles, and this is what a polycrystal is. I have lots of different grains that have a structure, it has order, but as these grains meet up, as it solidifies, as it crystallizes, they don't match up. So I end up with grains. And this picture D here is what we'd look at kind of on the macro scale. If I could zoom out, this picture, picture C, we would look at these as lattices, which would be kind of the atomic scale. I could see where each atom is. If we zoom way, way out, this is what we'd actually see, maybe even with an optical microscope. We'd just see different boundaries, and each one of these boundaries is a crystal. It has a very specific direction, and they might even have the same structure. So all of these grains might be face-centered cubic, but they just don't match up, and so they come to a point where there is a grain boundary. I'm going to draw a quick picture of this. We have a single crystal. Let me draw a little, let's say I have a cup here, and this cup is full of something warm, some warm material. Let's say that it's liquid, It's going to be a pure hot liquid. It doesn't have any impurities in it. It's just a nice pure hot liquid. What I'm going to do is I'm going to cool this. And so after some time, I'm going to cool. It's going to freeze. Because it's a pure material, I'm going to actually cool this one slowly. I cool it slowly. It's a pure material. It's going to be more likely to form a single crystal. What's going to happen is a part somewhere is going to start to crystallize in some specific direction. And it slowly, again, since we're removing this thermal energy very, very slowly, this is going to cause the rest of the atoms or molecules to follow suit and all crystallize in the same direction. So this is for a single crystal. What we're going to do is we're going to look at the next picture. What about for a polycrystal? So we'll do polycrystals over here. I have this same picture. I'm going to have some hot liquid, and I'm going to let it crystallize. In this case, maybe a couple other things are happening. Maybe this pure, or maybe this hot liquid isn't so pure. Maybe there are some impurities in it. Or maybe when I cool it a little faster. So I cool it maybe quickly. Well, as it solidifies, it's again going to crystallize because this is a material that wants to crystallize. But because I have some imperfections in here, it might start crystallizing around those imperfections. Or if I cool it quickly, I'm removing the thermal energy fast enough to where it doesn't have time to orient the entire batch of liquid as it cools. It cools differently in one spot than another. It starts solidifying in one spot compared to the other. There's not enough thermal energy to keep that motion going to allow things to line up. And so I might end up with a portion where we crystallize, let's say in one direction, we crystallize in another, maybe we crystallize in some other directions as well. So I'd end up with a polycrystal. It is crystallized. It's just the fact that it crystallizes in different directions because we cool it too quickly, or maybe the molecules that are crystallizing, it's difficult for them to move. Or maybe it's not pure and so it crystallizes around those impurities. There's lots of possible things that could be happening here. Now let's go back to our picture of pulling apart that graphite. It's going to work for any material. If I try to pull apart a single crystal, what we're going to see happening is I have a material, I'm pulling on it, and we need to remember that this material, even though we don't see it, has atoms, and it's made up of a lattice structure. And let me get it written in here. And there are going to be planes in here, some planes that are more densely packed. Let's say that this red plane here is densely packed together. It's a close packed plane, so those atoms do not want to move away from each other. I have another plane directly below it, and it would be the exact same plane structurally as the red one, except for it's just the next step down. The bonds between those two planes, though, are going to be weaker than those close packed planes that this red and green plane make up. So as I pull this apart, what's going to happen is the planes are going to slide. And again, this is slip. And as it slips, the material is going to start to deform. We could look at our FCC structure. And we could look at our unit cell for that. Let me see if I can draw it real quick. We have the unit cell, we have atoms in the center. Those should be touching. Let me see if I can redraw them slightly. That one is a bad one. I hope you can visualize what's happening. The front looks a little bit better than the rest of it. The top looks okay. That right-hand side is horrible. So what we could do is we could take different cuts of this, and I'm not necessarily going to draw all the cuts on this unit cell. The unit cell is ugly enough as it is. I don't want to start adding more things to it. But if I cut this with a 1-1-1 plane, I'm going to end up with something that looks like a triangle. And you can go back, watch the video, look at your notes. The 1-1-1 plane, we basically cut it completely diagonally. We cut this cube diagonally so that we end up with a triangular cross section. If we do this, we end up with a picture that kind of looks like this. Nope, not like that. Kind of like that. Where those are our atoms. So we have it. This is a very dense plane. This is our close packed plane for our FCC structure. Very, very little empty space. But if I were to try to cut this with a 0-1-1 plane, I'm going to use a different color so that these don't start running together. If I were to cut this with a 0-1-1 plane, that's one where I just cut it diagonally across the middle here, kind of like you're cutting a sandwich to make triangles. If I were to do the 0-1-1 plane, I would end up with a rectangle. And in this case, I would end up with something that looks like that. We could see that there is much, much more empty space. And so this is a spot where we could see that these atoms here aren't bonded very closely, and those bonds would be way more likely to break than what we have pictured here above it with the 1-1 plane. Lastly, we could, let's say, do a 0-0-1 plane. This would just be a face. We could cut our material so that we have this square face. And if we draw this, it looks like it's more densely packed than the 0-0-1, but it's definitely not as closely packed as the 1-1-1. So there are some of these planes that are more likely to stay attached, and more that are likely to not, and that they will break more often. So that is how a material breaks. First off, we have this slip going, and this slip plane is made up of planes that we can cut from our unit cell. And if we have a pure material, a single crystal material, this slip happens relatively easy. There's nothing really causing it to not slip. Let's take a look at a polycrystal. If I have this same type of material and I want to pull it apart, but let's say that I have multiple grains throughout here. So I have these are pictures of grains. And let me draw my little circles in here again. I am going to have some circles that line up in that grain. I'm going to have circles that line up in that grain. I'm going to have maybe some circles here. So all these planes are lining up. And let's take a look at this green and blue plane that I have here. As these slide, as I pull it apart, the blue ones are going to slide one way. The green ones are going to slide the other. But then what happens is it can only slide so far, because eventually we're going to meet up at this grain boundary right here. And at that grain boundary, this grain is going to have planes of atoms that are going in an opposite direction. So it's not going to be as easy for these to slide right through there. They'd have to break through this grain to keep moving. And this grain, since it's oriented differently, doesn't want to break in that direction. It would rather break or slide in some other direction. And since those directions aren't lining up, it's actually more difficult to break this material. We'll get into some terminology when we start talking about material properties in a few weeks. But the idea here is when I have a single crystal, once slip starts and occurs, there's nothing really that's going to stop it except for stop pulling it apart. But if I keep applying a force, it's going to continue to slip relatively easily. For a polycrystal, the more grains that I have, it's actually going to make it harder for this slip to propagate through the material, which actually makes it harder for the material itself to break apart. All right, so we want to talk about some differences in single crystals as opposed to polycrystals. We're going to have some terminology here. The terminology, one of them is isotropic. That means that it has a physical property that has the same value and measured in different directions. So it doesn't matter what direction something is occurring in, it's going to be the same value no matter what. Anisotropic means that the property is going to depend depending on what direction or orientation the material is at. So let's take a look at a single crystal and a polycrystal. And we'll look at some similarities and some differences. So my single crystal, again, I'm going to draw this in 2 dimensions because it's hard to draw in 3 dimensions without it getting too difficult to see what's happening. So I've taken this cross section of a material, and here are my atoms. We can see that it is a crystal because we have order in different directions. I could say there's an order in this direction, there's an order in this direction, there's an order in this direction. There's probably going to be an order in all different directions, even coming in and out of the screen. And again, our orientation really is arbitrary. We can pick that. But if I pick this direction as 0 degrees, and we could rotate this around some degree theta, what we can do is we could take some measurements. And a good way to maybe think about this is, let's say that I want to apply a voltage through this material. And so I apply a positive voltage on one end, I ground out the other side, and I want to see how voltage flows through this material, how electrons flow through this material. I have a nice set of order right along this 0 degree mark. And so electrons could hop from atom to atom relatively easily. Again, if I rotate this material a certain amount, then I have some good order where my electrons can flow through here. But what if I wanted to, let's say, pass my voltage that way? We could see that would be harder because the electrons would kind of have to zigzag through here to be able to get through my material. So if I were to plot this, make a graph here, I have the angle of my material and I have my property intensity. I'm just going to write prop INT for property intensity. So the intensity of whatever property I am. Right now we're talking about voltage, how easy it is for an electron to move through, but it could really be any property. What we would get is for a single crystal, we might have a high property intensity at one orientation, very high voltage, the ability for voltage to pass through in one direction. But as we rotate, it isn't quite as intense, and so it might drop. But then we get back to a point where we get some order and we have nice close atoms, and it might come back up, and we kind of get this periodic intensity for our property. And this is what happens with a single crystal. And because our property intensity, the property of our material, is going to correlate with the structure, and the structure is periodic. It has some symmetry in it, and so we'll see that symmetry as it propagates with our property. Now, if we have a polycrystal, we're not going to get this same picture. I'm going to have a material. I'm going to zoom out a little bit because it's very difficult to draw polycrystals with all these circles and show that we have a polycrystal. I'm going to zoom out, and let's say I have different grains, and this one I have going in one direction. I have this one going in another direction. And these are all in slightly different directions, or maybe vastly different directions, all of my grains here. As I try to pass, let's say, a voltage through here, in some directions, it's going to be very, very easy. That electron can flow very, very easily through. Let's say this middle grain here, if the voltage is going left to right or right to left, it might pass through very, very easily. But what if once I make it to this grain that's kind of on the left here, where the lines are almost vertical, it's going to be much, much harder for that property to go through, for that electron to make it through. So in this case, the property intensity kind of averages out. And if I were to draw this same graph, has the same axes, I'm just going to put an I here for intensity. We might not get any spot way up here where we get the property really, really well, but we're not going to necessarily get it at the very bottom either. It's going to kind of average somewhere in the middle across the entire graph. The smaller the grains, the more grains that we have, we're going to see it averaged out even more. And so for a single crystal, it's going to be anisotropic. For a polycrystal, it is going to be isotropic. It doesn't matter what direction we apply that voltage, it's pretty much going to work out no matter what. Now, this isn't necessarily 100% true, because if I have a material that has very, very large grains, just a couple grains throughout the material, I might still be able to see that in one direction it would be easier for something to move than the other because it doesn't average as much. The other one would be if I had a textured material. Let me draw one more here. And a textured material is a material that all the grains tend to kind of line up in particular directions. And it happens sometimes when you process a material, such as maybe rolling a material or working a material after it has solidified or crystallized. And I kind of maybe get these long grains throughout here. And as we work the material, they all kind of line up in the same direction. They aren't going to necessarily uncrystallize from a polycrystal and jump into a single crystal, but they're going to start lining up more. Again, if I pass a voltage one direction, it's going to act differently than if I pass it in the other. So a polycrystal, if it is an unworked polycrystal, we have nice uniform grains, and those grains are really, really small, then it is isotropic. But we do get some pictures where we do have some anisotropic. properties. We'll finish up the video by looking at some real-world examples of some things. If we look at stacks of cans, they can be stacked really in any way as long as it's a regular pattern, and we'd say that it has some type of regular pattern in all directions. So I could stack them directly on top of each other, next to each other, and in and out, or I could have them a little bit off-centered. And all these are valid ways to stack cans. There's obviously long-range order. So this is kind of an example of what a crystal would look like. Now, if I took these cans and I stacked them in a box, let's say these cans right here, this first set of cans were stacked in a box, and this is how they were stacked inside the box. We can see kind of in the background here that there are some boxes that are stacked up nicely, some off to the left-hand side as well. Right up here close on the right-hand side, there are some boxes that are still stacked up really nicely. This would be like a single crystal. We have order throughout the entire palette of boxes. The cans are all structured uniformly from the very bottom box to the very top box, to the box that's further behind, to one that's next to it, and so forth. Now, this mess of boxes in the middle, we can assume that the cans inside the boxes were all fit snugly and tightly, which means the cans inside the box are still organized. They're still stacked on top of each other. They still look like these cans on the top here inside the box, but the boxes are all oriented differently. And so this could be thought of kind of as looking like a polycrystal. Inside of each one of these boxes there is order and there's organization, but there is no long-term range throughout the entire pile here. Some of them are twisted one way, turned the other, upside down, rolled around a little bit in each direction. Same idea here with a stack of newspapers. Each one of these stacks of newspapers, you can see that the images and some of the text, you can see that they're all the same throughout a stack or throughout at least a chunk of a stack. So there is some order here. I see this one on the top, kind of the left-hand side. There's this reddish image here that maybe has 10 newspapers stacked, and we see that same reddish image at the same location for all 10 of those newspapers. There we have definite order. But the fact that all these bundles are flip-flopped back and forth, some are tipping over, again, there is order within each bundle, but all the bundles together are facing different directions, so this would be similar to a polycrystal. I do have a picture of some fruit here. Go to a fruit stand, somebody takes the time to stack it up all nice and neatly. We can see that we have some type of crystal structure here, but we've probably all been to some type of grocery store or fruit stand where things aren't organized well and they're just kind of flopped in there all randomly. We'll talk about things that are more random in the next video, but this video was just an overview of what a single crystal is compared to a polycrystal.